Hi there, happy Friday. So I got a video for you to cover lab 10B. I think you'll find this lab pretty fun. But first, I'm going to show you some of the solutions from the previous lab, lab 10A, this last problem with the barking deer. If you wanted to check your work, we have the proportions of land that are distributed in this region in China. And we multiply those proportions by the number of sites, 426, to get what is the expected counts. And of course, the observed counts are the habitat. So you could just say observed equals habitat to copy those over. And if you wanted to check your chi-square statistic, you get 284, which kind of seems like a big number, which is the case. This shows you that the counts differ quite significantly. There's very strong evidence that we can reject the null hypothesis that deer don't prefer a specific site over another. So one thing you'll find in R is a lot of statistical tests. There's one function that will do them. So everything we just did can be done in one line. If you put the observed counts in, habitat or observed, same thing, and then you put the probabilities from the null hypothesis, it does the exact same work. It finds the chi-square statistic. It knows the degrees of freedom is 4 minus 1. And then it finds the p-value is less than this number here. It means 2.2 times 10 to the negative 16th. It's 0.015 times and then 22. So it's basically 0. So good. Now that you have this code, if you want to do your test using this code for the test of goodness of fit, have at it. So then next is lab 10. 10B is another test that uses the chi-square statistic, but instead of one table, a one-way table where we have different categories, like you could see our observed counts here. This is a one-way table. The test of independence looks at two-way tables and says, are these two variables related to each other? So the way we're going to think about this first is look at a two-way table that I've just made up. Here's a two-way table. Tell me what's the probability of x1 occurring. We got two variables, x1, x2, y1, y2. The probability of x1 is going to be total amount of x1, which is 50. So 50 divided by 100. The probability of x1 occurring, given that y2 has occurred, that means we're looking at this column here, y2 has occurred. What's the probability of x1 occurring given y2? This should say y2 here. Typo. So 40 x1s out of 50 y2s, out of 50 total. Yeah. So there's two more problems. I'll let you do this one. Given y3. Oh, yeah, there's a typo in here. This should say given y1 occurs. Given that y1 occurs, what's the probability of x1 occurring? You get 10. You should get 10 out of 50. So this shows you that like x1 seems to be dependent on y, right? Because like whether or not y1 occurs, y1 or y2 occurs changes the probability of x1 occurring. That's what we're saying here. So based on this, are these guys independent? Are these things equal? Probability x1 occurring given different information? And the answer is no, like these seem different. So here's a table that's probably not independent, right? Like if you know x1 is occurring, if you know y1 is occurring, it's more likely that x2 will occur, right? And if you know y2 is occurring, it's more likely that x1 is going to occur. So let's think about what will happen if we want to balance this table. If we want to make these variables independent, like they don't affect each other. What do you think would happen in these values? Think about it. If they're equal probability for all things occurring, you can see that like x1 should occur half the time, right? So I'm going to put A here is 25, 25, 25, 25. Do you see how this table is balanced now? It's symmetric. And it looks like this is a case where things are independent. Okay, so now I'll give you this one. How would you balance this table? Where these row columns have to add up to 80, and these row columns have to add up to 20. These values no longer work. So we should say, in order for these two to add up to 20, I could put like 0 here, 20 here, and then if 20 was here, then I would have to put 30 here, right? To make them the columns 50. And if I put 0 here, I'd have to put 50 here to make the column add up to 50 and the row add up to 80. So that's one way you could make the table. But it's not independent, right? Like if y1 occurs, x1 is definitely not going to occur. It's never going to occur. But if y2 occurs, there is actually a much higher probability of x1 occurring. So to balance this, you should stop and think about like, how could I balance this table? How can I make it so that it's not independent? Think about that. So check that out. Here now it's balanced. You see like whether or not y1 and y2 occurs, x1 is the same probability, 10 over 50, 10 over 50. Here's an independent table. So when testing independence, our null hypothesis is going to be just this. Whatever makes our table balanced, that's the null hypothesis. Then the variables are independent. And so try this other case. What if it's looking like this? This is a little bit more tricky. How can we balance these guys? If I say 10, 10 here, and 40, 40 here again, it's no longer independent. Probability of x1 given y1 is 10 out of 10, 100%. But probability of x1 given y2 is 10 out of 90. There's 90 total y2 cases. So how do we balance this? Think about that. Think about how we might balance this table so the probabilities are not going to change. So here's the trick. What we want to have happen is 90% of the 20 go here. Okay, so what's 9.9 times 20? That's 18, right? And 10% of the 20 go here. That's going to be 2. And the same thing, 90% of 80 is going to be 36. And 10% of 80 is just going to be 8. Do you see how we found that? Now look there. Now look, the probability of x1 given y1 is 2 out of 10. The probability of y2 given, sorry, x1 given y2 is 18 out of 90. If you divide by 9, that's the same thing as 2 out of 10. Now it's independent, okay? So the actual formula for making these independent is just what we did. Oh no, here's another one. You should do this one. I'll leave 4 for you. And if you get stuck on 4, use the formula. Number 5, I'm going to give you the actual formula for finding the values. The expected counts are going to be the column total times the row total divided by n. You see how we got that? 10 times 20 divided by the total, 100. So there'll be 2 here, right? 10 times 20 divided by 100. Yep. And this one here will be C2 times R1 divided by N. We take the column total times the row total for that cell. Make this a little bigger. C3 times R1 divided by N. Right? And then if you copy that here and here, now we're looking at column row 2. That's the thing that changes. Row 2 here, row 3 here. Now look at it. This makes it look like you can see what's going on. Oh wait, this is not row 3. Undo that. There's not 3 rows. The third row is the total. Pardon me. Okay. Boo, boo, boo. Okay, this one's right. Copy that row. Undo all that. There we go. Okay, yeah. So row total times column total divided by N. So see, this is the first column, second row, it's C1 times R2 divided by N. Okay. That's a formula you can use for finding any cell in here. Like this cell, it's going to be C3, the column total, times R2, the row total, divided by 100. So 6 times 8 divided by 100, it's going to be 48. Okay, so use that formula to find out what the independent values will be here. This is where we balance the table. This is the null hypothesis. There is no difference in those. Okay, here's another way to see that formula. The expected value for each cell is the row total times the column total divided by the total number n. Okay, that's the background understanding for this test. If you got this, awesome. If not, like, okay, you can still do the test without understanding exactly why the null hypothesis is the way it is, but this section explains why we use the null hypothesis for independence, what we use. Okay, so here's an example of research of sellers. We want to know if people are selling something and the person selling is being maybe a little bit dishonest to make the sale. So here we go. We got a study where people are selling iPods that are known to be frozen. Have you ever bought like a, what do you call it, a refurbished phone? Yeah, they sometimes have problems, maybe. So or even just a used phone, like the researchers are selling these phones that are maybe been frozen in the past. Oh, they know this, but they're saying you get a 5% cut of the sale on top of like $10 for making the sale, or for just doing it. So whatever you sell the iPod for, you get a bonus. So we're going to see, is this going to cause bias in the participants? So the buyers, unbeknownst to the researchers, are collaborating to evaluate the influence of the likelihood of different sellers to disclose the past issues. So there's 3 different questions the buyers are asking. They say the general question, what can you tell me about the iPod? The positive assumption, does it have any problems? Does it? Or the negative assumption, what problems does it have? Okay, which one do you think is going to lead to the seller disclosing whether it has this problem with selling, like freezing? So here's the actual data. Of the people who asked the general question, what can you tell me about it? 2 people disclosed, 71 hit it. Okay, for the people that asked the question, does it have any problems? 23 disclosed and 50 hit it. And then for the negative question, 36 disclosed the problem, 37 hit it. So the question is, does it matter? Does this question change how the seller is going to respond? So, and this is kind of useful if you're buying a car. You could say, what can you tell me about the, actually, I just bought a car. What can you tell me about it? You could ask what, it doesn't have any problems, does it? Or what problems does it have? The car I bought actually had some problems, I found out. Like I took it to a mechanic. And if there is this difference, this is the question that you should ask, right? For buying something, if it causes the seller to disclose like the issue. Okay, so here's some things we can do with this information. Here's our mosaic plot. This makes it pretty clear, like disclosing the problem is in dark. Looks like it's going to cause, be more likely for the negative case. Okay, so it looks like there's a relationship, right, between these variables. So how do we test this? The test involves a hypothesis of, no, they don't matter. It doesn't matter which question you ask, they're independent. So whether or not the seller disclosed the problem is independent of what the seller asked. So the alternate question would be whether or not the seller disclosed the problem. What's the opposite of independent? Dependent. They're more likely to disclose it given certain questions. Which that's to say. So the expected counts based off our iPod sales. The expected counts, I'm going to put the iPod up here so we can see it. Expected counts for this. Oh, but we want to put the totals on there too. Add margins. We'll add the totals. We want those totals. Okay. So once you have the totals, you can see that the expected count for the first cell, the 1-1 cell, is going to be the column total times the row total divided by the total. So that's how we disclose it. And then this is the first row, second column, this cell here. We got to say 73 times the column total, the column total times row total 36 divided by 219. Oh no, 61. That's the row total. And this one, actually, you see these all should all be the same, right? The column total times the row total divided by the total. Okay, so that's for the first row. In the second row, let's see, it should be the column total times the row total, which is 158 divided by the total. So those values are the same all in the second row, since there's 73 people in each case. So 73 times D8 divided by 219. Okay, so that's the expected counts. Excuse me. And you could even mosaic plot this. Oh, did I do it right? Check my code. Mosaic plot. Oh, I have to do my no, let's try it. Yeah, mosaic plot. That's what I wanted to do. Undo. I want to do this. Mosaic plot on my expected values. Oh, do you see how like they're even now? Like each category is evenly distributed based off the column and row totals. So that's going to be my null hypothesis. These are the counts for my null. So my observed counts are here. My expected counts are here. And the chi-squared statistic is the same thing as before, but we have more cells, right? So the whole table, we're going to go observed minus expected, square it, and I got to put this here. Then divide by expected. That's what this formula says. And I'm adding over all the rows and columns, so I have to sum that up. So there's the sum of that. That's my chi-squared statistic. Brilliant. and if you don't have to like think about this formula if the above makes sense, but if you like the formula, this formula means always put the first index, this little I is called the row index, the J is called the column index. So OIJ is the observed count for the ith row and jth column, and EIJ is the expected count for the ith row and j column. That's kind of a standard notation for how we refer to things in a two-way table. Either way, once you get the observed and expected, it's the same chi-squared statistic. The degrees of freedom is a little funny. It's the number of rows minus 1 times the number of columns minus 1. So if we had 2 rows and 3 columns in this example, 2 rows, 3 columns, it's going to be 2 minus 1 times 3 minus 1. So just 2 degrees of freedom. So that you can use to plot your, to graph your chi-squared statistic. And we want to know what is the probability of getting something greater than what we observed. So we observed this value here. So we're going to say 1 minus p chi-squared. Since it's an upper tail, the degrees of freedom we found were 2. So there's our p-value for this test. Ooh, very low p-value. This means we reject the null, interpret the results. I'm going to let you guys do that since you now are becoming excellent statisticians. Write out what this means. If we reject the null hypothesis, which says these are independent, reject it in favor of the alternate, which says whether or not you disclose the problem does depend on the question. So that's actually really good information. Like when you're shopping, okay, what problems does this product have? Ask that question. Very good. Okay, so another cool thing about doing a chi-squared test with of independence is there's a formula in it. And in the formula, it can find the null values. Like the null values depend only on the values you put in. So if you put in your table, if iPod is your table, you run the chi-squared test, it does all the work for you. Notice we get the same chi-squared, the same degrees of freedom, and the same p-value. So this is nice. Once you understand a test, a program can often do the whole test for you. Now your job is just to interpret, hey, I got my p-value, what do I do with it? So very good. This is the end of my explanation. There's 2 more examples of conducting a chi-squared test. So your job is to repeat the above steps. You can even list A, B, C, D if that's helpful to you. Yeah, do that. And then at the bottom, I think I have work. So for part B, is that right? Part B, the 2 examples. Yeah, each example I run the actual test for you. Okay. And you can check your work then that way. Observed. Oh yeah, I have to run website here. So this is the website example, and this is the offshore drawing. So you can use that to check your work. Very good. Good luck. Come to class with questions on this on Monday. This will be due at the end of the day on Monday. And with that, have a good weekend. Look forward to seeing you next week.